Hello friends, this video on electric circuits part 8 is brought to you by examfear.com. No more fear from exam. Please make sure that you have watched all the videos till part 7 before going ahead with part 8. Let's look at the parallel combination of cells. Like how we studied about the series combination, let us have a look at the parallel combination. When I talk about parallel combination, as quite obvious, parallel combination would mean that all the positive terminals of all the batteries or cells will be connected together and all the negative terminals of the batteries will be connected together. So that is known as a parallel combination, such that the voltage or the potential difference across each cell is the same. That means, as you can see here, all the positive terminals are connected together and all the negative terminals are connected together. Schematically, you can draw it like this. Let us suppose these are your cells. So positive terminals of all of them are connected together and negative terminals of all of them are connected together. So the potential difference across each of these cells is the same. Right? So let us try to find out the equivalent resistance equivalent EMF in case of a parallel combination. So here also for the sake of convenience, let us assume that there are two cells E1 and E2 with internal resistances R1 and R2 connected in parallel combination. We assume that this cell is part of a closed circuit and a current is flowing through the cell. Since a current is flowing through the cell, internal resistance will be offered to the current. Okay, let us suppose some current is flowing through the cell. So now, let us write down the expressions as we wrote in the previous slide. So for the first cell with EMF E1, the potential difference between these 2 points, let us call this point as A and this point as B. So the potential difference between points A and B will be equal to E1 minus IR1. Now this current I is coming in, but when it reaches this point, it gets divided into two parts, right? This is I1 and this is I2. So I1 flows through E1 and I2 flows through E2. So here different currents flows through different cells. So V will be equal to E1 minus I1 R1. Similarly, for the second cell E2, V will be equal to E2 minus I2 R2. Notice an important thing here. Here the potential difference between these 2 points A and B will remain the same. Therefore, your left hand side is the same. But here the currents are different for the two cells. And another relation which we can see from the figure is I is equal to I1 plus I2. Right? So now, what do we see from here? So from this expression, we get I1 is equal to E1 minus V divided by R1. And from the next expression, we get I2 is equal to E2 minus V divided by R2. Right? So in this expression, we will put the values of I1 and I2. So I will be equal to E1 minus V by R1 plus E2 minus V by R2. So this can be written as E1 by R1 plus E2 by R2 minus V into 1 by R1 plus 1 by R2. So this is the expression for current. Now, here also, let us write it in the form of V. So this expression can further be written as V is equal to I divided by 1 by R1 plus 1 by R2 plus E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. So this is simple mathematics. Here I is equal to E1 by R1 plus E2 by R2 minus V 1 by R1 plus 1 by R2. So from this I wrote it in terms of V. So I got this expression. Now let us assume, so let us name this equation as equation 1. Now let us assume that instead of these two EMFs, we replace these two EMF with one EMF, that is with one cell. Instead of these two cells E1 and E2, we replace them with E equivalent. So now we will assume that, E equivalent instead of E1 and E2. So how will my circuit look like? My circuit will look like somewhat like this. Let us say this was point A and here I have E equivalent whose internal resistances are equivalent, and this is point B. Right? So now we don't have that parallel combination thing at all. So in this case, what can we write? In this case, we can write that the potential difference between point A and B, that is V, is equal to E equivalent minus IR equivalent, right? So now if you compare this equation 2 with the previous equation which we found, that is equation 1, that is this equation, then what do you get? In both the cases you get V is equal to E equivalent, which is nothing but this bigger term, minus I into R equivalent, that is I into R equivalent, which is this entire term. Right? So let us try to write it in this form. So we have to compare these two expressions. So let me write the expression 1 here itself. That is V is equal to I divided by 1 by R1 plus 1 by R2 plus E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. So if you want, you can simplify it further in this way, that I is equal to I into R1 R2 divided by R1 plus R2 plus E1 R2 plus E2 R1 divided by R1 plus R2. Right? So now if you compare this expression with this expression, what do you get? V is equal to I into R. So that R equivalent is nothing but R1 R2 divided by R1 plus R2. And what is E equivalent? E equivalent is nothing but this term, that is E equivalent is equal to E1 R2 plus E2 R1 divided by R1 plus R2. So this is what you get in case of a parallel combination. Look at the scenario where n cells are connected in parallel. So we will look at it in the similar way as we did for the series combination. Let us suppose there are n cells which are connected in a parallel combination across an external resistance R. EMF of each of these cells is E, and the internal resistance of each of them is R. Right? So here first we will calculate the effective EMF of the circuit. So what will be the effective EMF of the circuit? It will be E. Here the effective EMF of the circuit is E. So how do we get this effective EMF? In the previous slide, I calculated the equivalent EMF of the circuit, which came out to be E1R2 plus E2R1 divided by R1 plus R2. So here if you look at this circuit, R1 is equal to R2 is equal to R, and E1 is equal to E2 is equal to E. So if I put these values, we will get E equivalent as 2ER divided by 2R, which comes out to be E. So the effective EMF of the circuit is E, right? And what is the total resistance of the circuit? So the total resistance of the circuit will be equal to the external resistance plus the equivalent internal resistance. And what is equivalent internal resistance? That is nothing but R1 R2 divided by R1 plus R2. So here R1 and R2 is both R. So this will be R square divided by 2R, which comes out to be R by 2. So now by mistake here I assumed that there are 2 cells, but there are n number of cells, right? So this will be R1, R2, R3, R4 and so on. That means R multiplied n number of times, right? Similarly here instead of R by 2, like had there been 2 cells, I'm sorry, it was my mistake that I told it this way, but assume it this way. Here I considered it for 2 cells. Even if it is n cells, then what will be E equivalent? For n cells, it will be NER divided by NR. So that will also come out to be E. Similarly, R equivalent for n number of resistances will not be R by 2. Instead, it will be R by N, because the number of resistances is N, right? So what will be the total resistance? Total resistance will be equal to capital R plus R by N. So let us calculate the current through the circuit. So the current through the circuit, that is current through the external resistor R. This current will be equal to the effective EMF divided by total resistance. So what is the effective EMF? That is E, and total resistance is R plus R by N. So this will be NE divided by NR plus small r. So this will be the current which will flow through the external circuit. Now here also we can have 2 cases. The first case where capital R is very, very small, that is external resistance is very small. In that case, what will happen? In that case, current will be equal to NE divided by R. So current is N times the current due to a single cell. Second scenario where external resistance is very, very greater than the internal resistance. In that case, the current can be written as NE divided by NR. So this will be equal to E divided by R. That means the current through the external resistance is equal to the current due to a single cell, right? So these are the 2 important things which we concluded from here. I hope I didn't confuse you here in this part. I mean, it is very simple. With the help of E equivalent and R equivalent, you can calculate it for yourself, right? Okay. So now that we have understood the grouping of cells in series and parallel, it is time to solve some problems, because based on the combination of cells, we should be able to solve certain kind of problems. So what did we observe till now? So let us look at our observation. Thank you. Please visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thank you once again.